Welcome to the first lecture on completing the square. My name is Yuan Chen. I'm the foundation year tutor at Aberystwyth University, and I hope you will enjoy the following series of lectures. So to start with, we go back to fairly elementary maths and try to simplify and solve quadratics. So using completing the square, let me draw for you an initial quadratic. So this is the familiar U shape. Here's an axis. There's a quadratic. And let's just say that this is y equals x squared. And the problem we want to solve, so in mathematics, we often start with a problem. How do we solve the equation x squared equals c for some constant c? For concreteness, we might try c equals 9. So you may know, of course, the solution is just plus or minus 3. But geometrically, we're saying that we're looking for the intersection of this curve with the straight line, the constant line, y equals c. So we can see that the solutions we're looking for are the x-coordinates. Let's label my axis. We're looking for the x-coordinates of these solutions. So from the picture, if c is greater or equal to 0, we see there are two solutions, or possibly two repeated solutions. So there's root c and minus root c. In our example case, we just get plus or minus 3. So what about solving problem 2? How about x plus k squared equals c? Now this time k is some other constant k, and this shifts solutions by minus k. So we can see that here, if previously we had x as plus or minus root c, we get here that x plus k is equal to plus or minus root c. That is, to be more precise, it's either equal to, the solution is either equal to root c or minus root c. So x is equal to root c minus k or minus root c minus k. And what this does is just shifts the whole curve by k to the left. Let's call that minus k. And again, we can see that if we wanted these new solutions, we want the x-coordinates of these intersection points, which are these points moved as well. Everything moves to the left. So if we do another small example, so we have, let's say, k equals 4, and c is equal to 9 as before. We get x plus 4 squared equals 9, which implies x is equal to minus 1 or minus 7. Hopefully you can plug those in and see that this is the case. Let's do 3 more general solutions, general examples, and start with the first. So this time, let's find the solutions, or roots, of 2x squared minus 4x minus 3 equals 0. It's quite similar to above, but now this time we have a constant factor in front of the quadratic term, and we want to arrange into this familiar form that we already have. We already solved this x plus k all squared equals c. So we solved that already, so let's try that. So let's get rid of the factor. And so we could divide through by 2 on both sides to obtain remember that we can only divide by 2 because we're seeking just the roots of this equation. Now completing the square is where I put into the format like before. So here I can see that this is x minus 1 squared. But when I expand this out, I get an extra 1, so I need to cancel that off. So if I expanded this, note that so we need to kill off the extra term that we ended up with. That gives us this minus 1 squared. And so this is exactly the same format as above. In star, this time with k is equal to minus 1 and c is equal to 5 over 2. And so the final solutions, and we can just leave them precise, x is equal to 1 plus root 5 over 2, or 1 minus root 5 by 2. Example 2. So this time we want to solve the general quadratic formula. This is an algebraic usage of completing the square. So we solve. So this time, note earlier we had some constants, 2 and 4, or minus 4 and minus 3, but this time we want to solve the general quadratic formula, which is solving the general quadratic equation, ax squared plus bx plus c equals to 0. Now, to make this interesting, we want the first term to be non-zero, so a is non-zero, and for reasons we'll get to later, we want this particular factor to be greater or equal to 0. It means that there are solutions. This corresponds to our diagram earlier of there being a solution when I intersect my quadratic with some constant. It just means that there is some solution. So let's call these conditions 1 and condition 2. So 1 allows us to divide by a, and we get that x squared plus b over ax plus c over a is equal to 0. And now we complete the square. It's called completing the square because we were making these separate terms into a square term. So what we need is to have half of this middle term, and then we subtract off that extra term. that's created as before. And this implies that when I add together these two constants, so this is where we see the importance of the second condition. It means I can square root the right-hand side. So taking the square root, I get that x plus b over 2a is either the positive or the negative of the right-hand side. So plus or minus this term. And so finally, we get the familiar quadratic formula. So the roots of this general quadratic equation are plus or minus, are this constant term, which is minus b over 2a, plus or minus this term. I took the 2a to the outside. Let's end with one more example. Usually these videos are going to be between, let's say, 7 and 15 minutes, depending on the length of content. So we're going to do a simpler example, and we're going to find some extremal values of this function. So let f of x be a quadratic, that's x squared plus 6x minus 5. So we seek the minimum value of f and the value of x. So the input value x, where this is obtained. So those of you looking ahead, you can of course use calculus, which finds turning points, therefore extremal values. But let's use completing the square. So using the same familiar process, we get that it's x plus 3 all squared minus 3 squared minus 5. So this term here is always non-negative, and therefore this term over here must be the minimum value. And it's attained when x plus 3 is equal to 0, i.e. x is equal to minus 3. So the picture would be something like, here's a sketch. At minus 3, it reaches the value of minus 14. And note that there's a symmetry along this axis, because this term is symmetric. And let me see if I can draw this roughly correct. Looks something like this. And here we know when x is equal to 0, well, these terms vanish and it's minus 5. So this is a graph of this function. So we should be able to, if we want, also solve for these solutions where it intersects the x-axis. Maybe I leave you to do that. Perhaps as a bonus, so where is f greater than 0 and where is f less than 0?